Welcome to the Deep Dive. Today we're taking a fascinating leap into the world of artificial intelligence.
Yeah,
Specifically, how researchers are now able to automatically generate incredibly realistic 3D dance motions.
yeah, it's pretty wild stuff.
Think about the implications for animation,
Yeah.
for creating truly immersive VR and AR experiences, maybe even for programming robots to move with, a sense of grace.
Right. All potentially without needing painstaking manual choreography for every single step.
Exactly.
It's a truly exciting frontier. But as you can imagine, teaching a computer to produce dance that not only looks natural, but also, perfectly aligns with music, offers a diverse range of styles and movements, and respects the laws of physics.
Yeah.
Well, that presents some really complex challenges.
Absolutely. And what we've seen so far, it often has limitations, doesn't it? Existing methods can sometimes fall short on capturing those subtle nuances of realistic human movement.
That's true.
And maybe more importantly, they often lack flexibility when it comes to editing.
Yeah, the editing is a big one.
Imagine you want to adjust a dance based on a specific beat in the music, or shift the style from, say, ballet to hip-hop, or even just tweak the position of a hand.
Right.
Many current systems just struggle to accommodate those kinds of nuanced edits.
That very lack of editability is a significant hurdle for creative professionals. I mean, choreographers, animators, game developers,
Yeah.
they thrive on iteration, right?
Yeah.
On being able to experiment with different ideas and precisely refine movements until they get exactly what they want.
Well, that brings us neatly to the groundbreaking work we're diving into today. Our source material introduces a new framework called DanceMosaic, and its creators are claiming it can overcome these limitations. They say it can generate high-fidelity dance quickly, while also offering a really impressive suite of editing capabilities.
And what's particularly compelling, I think, is their approach to tackling that editability problem head-on.
Okay.
They're suggesting a system that allows for edits based on a really rich variety of guidance, signals everything from the music itself
Right.
to specific poses you might want to enforce, even textual descriptions of the desired actions, or like the dance genre.
Text, music, pose.
Yeah.
Oh, wow. So in this deep dive, our mission is to explore exactly how DanceMosaic achieves this.
Let's do it.
We'll be looking at the core innovations that set it apart from previous attempts. And most importantly for you listening, we want to provide a clear, sort of intuitive understanding of this really cutting-edge tech.
Sound good.
Okay, let's unpack this. What's the central concept behind DanceMosaic?
Okay, so the fundamental idea hinges on what they call a multimodal masked motion model.
Right.
Think of it as a sophisticated AI that learns to connect various forms of input, text descriptions, musical cues, information about body poses, with the generation of high-quality dance movements. It essentially achieves this by combining a model that can translate text into motion with these specialized adapters that allow it to understand and incorporate music and specific poses.
Multimodal, meaning it can process and understand these different types of data all at once. That makes sense. Now, masked motion model. That sounds intriguing. What's the significance of the masking part?
Ah, yeah, that's where their progressive generative masking training comes in.
Okay.
Picture this. The model is shown examples of dance movements, but certain parts of that movement which they represent as motion tokens.
Tokens. Like
Yeah.
little snapshots of the pose.
Exactly, like snapshots of the pose at different points in time are intentionally hidden or masked. So the model's task is to learn to predict these missing tokens based on the guidance it's given. The text describing the dance, the music playing, and any specific pose constraints you might give it.
So it's almost like a fill-in-the-blanks exercise, but like for dance movements.
Precisely.
By learning to predict those masked movements under different conditions, a waltz versus a tango, a graceful arm versus a sharp kick, it starts to grasp the complex relationships between the instructions and the actual dance.
Exactly. And the progressive part of the training is also really key here.
Oh, so.
It means this learning process happens in stages. It gradually introduces and refines the model's ability to understand and respond to each type of guidance text first, then maybe music, then pose.
Right.
This step-by-step approach helps the model learn these complex relationships effectively without getting sort of overwhelmed by too much information all at once.
Like building blocks. Makes
Yeah.
sense. Okay, here's where it gets really interesting for me. How does DanceMosaic make sure that the dance motions it generates are actually, high quality and truly align with all those different types of guidance?
Yeah, good question. They use a couple of really clever techniques for that. One is called multimodal classifier-free guidance, or CFG.
CFG.
This is basically a method to amplify the influence of each guiding signal, the music, the genre from the text, even a specific pose you want during the actual generation process.
Amplify. How does it do that?
Well, it works by essentially comparing what the model produces when it has all the guidance versus what it produces when it's missing a particular piece of guidance. And then it emphasizes the differences in the direction you want it to go.
So if you really want a dance to hit the strong beats in the music, this CFG helps push the model towards generating movements that are tightly synchronized with those specific beats.
Exactly right. It's like giving the music a louder voice in the conversation the model's having with itself about how to make the dance.
Okay, that's one technique. What's the other?
The other key technique is inference time optimization. Now, this happens after the initial dance sequence has been generated.
Right, like a refinement step.
Exactly. It allows for further refinement of the individual motion tokens, specifically to make sure they better align with any precise pose constraints that were provided. Think of it as a final polish.
Okay.
To make sure every joint and limb is exactly where it should be based on the guidance.
Gotcha. The research paper really emphasizes that DanceMosaic is the first method to use these generative masked models for achieving this level of high fidelity and editable dance. Why is that such a big deal?
Well, it's a significant step because these generative masked models have already shown remarkable capabilities in other creative AI areas like generating realistic images or coherent text.
Right, like DALL-E or GPT.
Precisely. So by adapting this powerful framework to the challenge of dance, DanceMosaic can leverage those inherent strengths in producing high quality and diverse outputs.
Okay.
And furthermore, the very nature of a masked model just lends itself well to editing. Because parts of the motion are represented as these masked tokens, you can essentially just mask out a section you want to change and then regenerate it based on new or maybe modified guidance.
That makes the editing much more direct.
Yeah.
And these multimodal adaptation and guidance modules, they keep mentioning what are they actually doing, sort of, behind the scenes.
Okay, so the adaptation modules are essentially the music and pose adapters we touched on earlier.
Right, the specialized parts.
Exactly. They act as the specific mechanisms that allow the model to take in these non-textual forms of guidance, the music, the desired poses, and integrate them into its core understanding of how text relates to movement.
Okay.
The guidance modules, on the other hand, like the classifier-free guidance and then inference time optimization, those are the strategies used during the actual generation process to ensure the final dance output really faithfully adheres to all the various pieces of input you gave it.
Got it. Let's maybe dive a bit deeper into these core components then. First up, the dance tokenizer and the text-to-motion model. What specific roles do these play?
Okay, yeah. The dance tokenizer plays a really pivotal role. It bridges the gap between the continuous fluid nature of 3D dance movements.
Which is complex data.
Very complex.
Yeah.
And it bridges that to the more discrete kind of language-like tokens that the model can actually process effectively.
Okay. How does it do that?
It uses a technique called VQVAE, which learns a kind of code book of representative dance poses.
A code book, like a dictionary of poses.
That's a great way to think about it. So instead of the model dealing with raw frame-by-frame data of tons of joint positions, the tokenizer converts these continuous motions into a sequence of discrete tokens. Essentially, a sequence of the most representative poses from its learned codebook.
Okay, so it's like transforming a complex dance into a sequence of specific pose words chosen from a limited vocabulary. This discretization, why is that so crucial?
Exactly. It's crucial because this discretization allows the model to learn probability distributions over these discrete tokens conditioned on the input guidance.
Right.
This makes it much more feasible for the model to generate a diverse range of high-quality motions by basically probabilistically sampling from these learned distributions of pose tokens.
So it simplifies the problem space.
Massively. It moves away from the complexities of continuous motion data to a more manageable language-like representation. It's a key insight that's driven advances in other generative AI fields too.
Okay. And then we have the text-to-motion model, or T2M.
Yeah.
How does that build on this tokenized dance representation?
Right. So the T2M model is built on a transformer architecture.
Like in language models.
Exactly like in language models. Transformers are really good at understanding and generating sequences. It takes the sequence of motion tokens from the tokenizer. And it also incorporates text embeddings. Now, these text embeddings come from a pre-trained model called CLIP.
CLIP, I've heard of that, language and images.
Exactly. Contrastive language image pre-training. It's learned the relationship between text and visual concepts, which turns out to be really useful here for understanding dance genres described in text.
Yep.
So these embeddings can capture information about the style of dance or specific actions described in the text prompt. The T2M model then learns to predict which motion token should come next in the sequence, given that text input and maybe some of those masked out tokens we talked about.
So if I type in, like, a person gracefully dances ballet, the model uses the CLIP embedding of that text, along with maybe some initial masked motion tokens, and tries to predict the subsequent unmasked tokens that would actually look like ballet movements.
Precisely. And it's trained using something called cross-entropy loss. Essentially, that just means the model is constantly trying to maximize the probability of correctly predicting those masked tokens based on the text it's given.
Okay, that makes sense. Now let's bring in the music. Tell me about the music adapter. How does that fit into the system?
Right. The music adapter, its main job is to enable the generation of dance motion that's conditioned not just on text, but also on the accompanying music.
The rhythm, the beat.
Exactly. It achieves this by extending the existing T2M model with a parallel, trainable, music-guided masked model.
Parallel. Okay.
The architecture is inspired by something called ControlNet, which was originally for images, but they've adapted it specifically for this task of multimodal motion synthesis.
So it's like having a dedicated pathway inside the AI that specifically processes the music and learns how that music should influence the final dance moves.
Exactly that. And what's crucial here is that this parallel structure lets the model effectively fuse the text and music inputs without, messing up the overall realism of the generated motion.
That seems important. How does it get the musical information in?
They use another pre-trained model called Jukebox to extract music embedding.
Jukebox. Okay.
These embeddings capture various aspects of the music rhythm, melody, that sort of thing, and then they're directly added to the sequence of motion tokens.
Added directly. Wow.
Yeah, it provides a very direct connection for learning the temporal synchronization between the dance and the music's rhythm and beats.
So adding the music embeddings right onto the motion tokens, that sounds like a very direct way to ensure they're aligned in time. Does that help make the dance feel synchronized?
Absolutely. It provides that direct connection for learning the timing. And when they train this music adapter, they don't just rely on that cross-entropy loss for predicting the tokens.
What else?
They also incorporate additional kinematic losses.
Kinematic? Like physics?
Yeah, basically.
Right.
These losses specifically evaluate aspects of the generated motion, like the positions of the joints, their velocity, acceleration, and even whether the feet are making realistic contact with the ground. Foot skating.
Foot skating.
Yeah.
The bane of bad animation. So these kinematic losses are specifically designed to ensure the physical plausibility, to make sure it looks like a real human could actually do it.
Exactly that. Things like minimizing that unnatural foot sliding, ensuring smooth transitions between poses, and just generally making the whole sequence look physically believable. Now, to integrate these kinematic losses, which operate in the continuous world of 3D motion, with the discrete token space the model uses.
Yeah, how do they bridge that gap?
They use a clever technique called Gumbel softmax sampling. It essentially makes the process of selecting the discrete motion tokens differentiable.
Differentiable, meaning the math works out for training.
Precisely. It allows the gradients, the error signals from these continuous kinematic losses to flow back through the model during training, even though it's working with discrete tokens.
That's really ingenious. Okay, we've covered text and music. Now let's talk about the pose adapter. How does this component allow for that precise editing of specific dance movements?
Right, the pose adapter. This is specifically designed for that fine-grained editing of particular joints or even whole regions of the body, while making sure the overall dance remains coherent and stylistically consistent. Its architecture is pretty similar to the music adapter, another parallel mask transformer. It takes spatial pose constraints as input-like, the desired 3D positions of specific joints at specific moments.
So I could say, I want the left hand exactly here at this beat.
Exactly like that. You could input the precise XYZ coordinates for that hand at that specific frame, and the pose adapter guides the generation process to respect that constraint.
Can you constrain multiple joints?
Yep. You can specify constraints for a subset of key joints, while the movements of the other body parts remain editable and are generated by the model based on the other guidance signals, like the music and text.
And how does it incorporate that pose information?
Similar to the music adapter, the input pose signal is first projected onto a set of latent pose tokens, which are then combined with the regular motion tokens inside the transformer architecture.
Got it. And the training for this pose adapter, how does it learn to actually follow these spatial instructions?
It also uses that cross-entropy loss to predict the masked motion tokens, conditioned on the text, the motion sequence, and the pose signal.
Okay.
But crucially, they also add an extra discrepancy loss.
Discrepancy loss.
Yeah, this loss function specifically measures and minimizes the difference between the input pose constraints you gave it and the actual pose information that's extracted from the motion sequence the model generates.
Ah, so it directly checks if the output matches the input constraint?
Exactly. It ensures the resulting dance really adheres to the specific poses you dictated.
We've discussed how each of these parts is trained, but the paper mentions multimodal progressive training. Why is it necessary to train them in this specific sequence? Text first, then music, then pose.
Yeah, the progressive training is a really crucial strategy because when you're trying to optimize a complex model with multiple different loss functions, the music loss, the pose loss, the main prediction loss.
Right, lots of goals.
Exactly. You can often run into conflicts where the adjustments the model needs to make to satisfy one loss function might actually hurt its ability to satisfy another.
Like pulling in opposite directions.
Precisely. These competing goals can make the whole training process much less efficient and could lead to, well, suboptimal results.
So how does the progressive approach fix that?
They use a stage training approach. First, they train the core text-to-motion model on a big dataset of text-annotated dance motions. Get that foundation solid.
Okay.
Once that base model is well established, they freeze its parameters, basically. Stop updating its weights.
Knock it down.
Yep. Then they train the music adapter using dance motions synchronized with music, adding in the music guidance and genre prompts.
Right.
Finally, they freeze the T2M model again and train the pose adapter on dance data that includes pose information and genre prompts.
So layer by layer.
Exactly. This incremental approach helps mitigate those gradient conflicts and allows each modality-specific branch music, pose, to be trained more effectively without messing up the learning of the parts that were trained earlier.
That makes perfect sense. Build a solid foundation, then carefully add and train the specialized bits. Now, when it comes to actually generating a dance, the inference stage, how does DanceMosaic bring all this learned knowledge together?
Okay, inference. That's where the multimodal guidance at inference comes in. They use two main techniques here. The first, as we touched on, is that multimodal classifier-free guidance, the CFG.
Right, the amplifier.
Exactly. It extends the basic idea of CFG, which is common in diffusion models, to handle multiple conditions simultaneously: music, genre from text, and pose constraints.
Remind us again how CFG actually works in practice here with multiple inputs.
Essentially, during generation, the model calculates the output in parallel ways.
Right.
Once with all the guidance signals, text, music, pose, active, and once without any specific guidance, unconditional.
Okay.
It then combines these outputs using a weighted average. And the weights for each modality, text, music, pose, determine how much influence each type of guidance has on the final motion.
So you can tune those weights, like turn up the music influence or the pose influence.
Exactly. They have specific scale factors you can adjust. So by tweaking those weights, you can make the dance more strongly influenced by the music's rhythm, perhaps, than by the exact text description. And the math basically shows the final output logits are a weighted combo of the unconditional output and the individual conditional outputs for each modality, scaled by their weights.
And these logits, they determine the final tokens.
They're converted into probability distributions over the possible motion tokens. Yeah. And that guides the selection of the next token in the sequence being generated.
And that leads to the iterative process of generating the whole sequence, right? Step by step.
Yes. They start with a completely masked sequence, just blanks. Then, over a series of iterative steps, they sample the actual pose tokens based on those probability distributions shaped by the CFG. The key thing is, during this sampling, if a token is sampled with low confidence.
Meaning the model isn't sure.
Exactly. If it's not very confident, that token gets remasked and resampled in the next iteration.
It gets another chance.
Right. This process of remasking and resampling continues for a set number of iterations, following a schedule that gradually reduces the amount of remasking over time.
Why reduce it over time?
Because as more of the sequence gets filled in, the model has more context and can make better predictions. This allows it to refine its initial guesses, especially early on when it doesn't know much about the overall motion yet.
Sound like a very deliberate, controlled way to generate the dance, allowing for refinement. What's the second inference time technique they use? The pose-guided inference time token optimization? That's quite a mouthful.
Chuckles slightly. It is a bit, yeah. But it describes a really effective method for further refining the generated motion to better match any specific pose constraints you gave it.
Okay, so even more refinement after the main generation.
Exactly. Because even with the pose adapter and the CFG, the influence of sparse pose signals like constraints on just a few joints or only at certain time points might still be relatively subtle compared to the stronger influence of, say, text or music.
Right, they might get drowned out.
Potentially. So this optimization step uses gradient descent.
Standard machine learning tool.
Right. To directly adjust the embeddings, the internal representations of the motion tokens in the model's latent space. The goal is just to minimize the difference between the input pose constraints you provided and the actual pose present in the generated motion.
Okay.
What's particularly clever here is that during this optimization, the entire DanceMosaic neural network stays frozen.
Oh, interesting.
Yeah. Only the embeddings of the input motion tokens are treated as trainable variables. This speeds up the optimization process massively.
Right, less computation.
Exactly. Once these token embeddings have been tweaked slightly, they then influence the final sampling probabilities for the generated dance.
So it's like fine-tuning the pose in that hidden representation after the main generation to make it even more accurate to the instructions.
That's a perfect way to put it.
Okay, so all these intricate pieces work together to first generate an initial dance, then refine it to match text, music, and pose inputs. Now, the paper highlights some specific applications of DanceMosaic. What practical things can this tech actually do?
Yeah, they showcase some cool stuff. One really interesting application is spatial body part editing.
Okay.
Because of the pose adapter and that inference time optimization, DanceMosaic allows for very precise control over specific joints or body parts within a dance sequence. You can iteratively refine the motion, adjusting the movement of designated editable joints while making sure the overall dance stays coherent and synchronized with the music and the original text prompt.
So I could maybe tweak just the arm movements in a generated salsa dance without messing up the legwork or the timing.
Exactly that. Precise, localized control.
Cool. Another application they highlight is temporal body part editing. How does that work? Editing over time.
Yeah. Using the generative masking process, you can essentially fill in missing segments of a dance motion.
Oh, like in painting for video?
Kind of.
Whoa.
Or you can create smooth, natural transitions between key poses that you define by strategically placing those MS tokens within a sequence.
Right.
The model can reconstruct the missing parts in a way that maintains temporal consistency and rhythmic synchronization with the music and the text guide.
So if I had a few key poses defined at different points in time, I could ask the model to intelligently and musically fill in the movements between those poses.
That's a perfect analogy for it, yeah.
Neat. And the third key application they show is long dance generation. This sounds particularly tough for AI. How does DanceMosaic handle creating longer sequences?
Right. Generating long, coherent sequences is often tricky. DanceMosaic demonstrates a remarkable zero-shot capability for this.
Zero shot, meaning it wasn't explicitly trained on super long dances.
Exactly. It can generate shorter, coherent segments of dance, maybe a few seconds long each. And then it uses that masked token reconstruction process we talked about to create fluid and natural transitions between these segments. It ensures each segment flows seamlessly into the next, conditioned on the adjacent sequences.
Ah, so it stitches them together intelligently using the masking.
Precisely. This avoids that common problem you see where you try to just stick shorter clips together and get abrupt cuts or weird shifts in style.
That's really useful for creating more extended performances. It bypasses a major hurdle needing huge data sets of long, continuous dances.
Exactly. It's a more modular approach to creating movement.
Now, let's get to the proof. How well does DanceMosaic actually perform? The paper has a whole section on experimental results. What were the big takeaways?
Okay, yeah, they tested it rigorously. They used several large public dance dataset, Fine Dance and AS+, plus were the main ones.
Okay.
And they also used human ML3D for pre-training the tokenizer and the base T2M model.
Right.
On the Fine Dance dataset, DanceMosaic achieved state-of-the-art results across a range of really important metrics.
Such as?
Well, they showed significant improvements in overall dance quality, measured by things like FIDK and FIDG.
Okay, what do those measure, roughly?
They basically assess the statistical similarity between the generated dances and real human dances. Lower scores are better, meaning they're closer to reality.
Got it. Better quality. What else?
It also showed higher motion diversity. meaning it's capable of generating a wider, more varied range of dance movements compared to older methods.
More creative, less repetitive.
Exactly.
And what about that crucial point? How well did the generated dances sync up with the music?
Good question. So it achieved the second best score on the beat alignment score, or BAS.
Second best, not first.
Not first. But the researchers emphasized that the really big gains they got in overall motion quality weren't achieved by sacrificing music sync.
Ah.
It still maintains a very strong and compelling connection to the musical rhythm. It didn't trade off sync for quality.
That's a really key balance to strike, isn't it? You want great movement that also feels connected to the music.
Absolutely essential.
What about physical realism? Did the dances look, physically possible? Did they avoid that foot skating?
Yes, they looked at that using the foot skating ratio, or FSR. DanceMosaic achieved the best FSR score among the methods compared, indicating a very high degree of physical realism, less foot sliding. And impressively, it also showed significantly faster inference speeds compared to many other top dance generation approaches.
Faster generation is always a huge plus for practical use.
Okay, what about the other data set, AST+++? Similar results.
Pretty similar story on AS++, Bo. They used a slightly different quality metric there called the Physical Foot Contact Score, PFC, which focuses specifically on how plausibly the feet interact with the ground.
Okay.
DanceMosaic got the best performance on PFC there, too. It also showed notable improvements in diversity while maintaining a competitive beat alignment score.
So it seems consistent across different data sets and different ways of measuring performance.
Yeah, overall, it consistently demonstrates strong performance and often surpasses the previous state of the art.
The paper also goes into detail on ablation studies. What important insights did those experiments give us about how the different pieces of DanceMosaic contribute? Right. Ablation studies are great for understanding what each component actually does. They basically remove parts of the system one by one and see what happens to the results.
Okay, what did they find?
For instance, they looked at the effect of that multimodal classifier-free guidance, the CFG.
Mm-hmm.
Their findings showed that removing the parallel decoding part of CFG led to a significant drop in motion quality. So that really underscores its critical role.
Okay, so CFG is vital. What about the different guidance types?
They also found that removing the music guidance had the most detrimental impact on the realism of the generated dance.
Wow, more than text or pose.
Yeah, more than the others in terms of realism. It highlights just how essential music is for creating believable movement in this context. But overall, the full DanceMosaic model with everything included.
The whole package.
Yeah, the whole package consistently achieved the best results, showing that all the parts work together synergistically.
And did they look at how sensitive it is to the amount of music guidance, like how much weight you give the music?
They did. They experimented with different scaling factors for the music guidance. They found that increasing the weight generally improved quality, diversity, and beat alignment, but only up to a certain point.
Diminishing returns.
Exactly.
Right.
Beyond an optimal point, cranking up the music guidance didn't help much more and could potentially even hurt things slightly. So there's a sweet spot for balancing music against the other factors.
Makes sense. What did the ablations tell us about the pose adapter and that inference time token optimization, especially for the editing features?
Yeah, those results were clear. The inference time token optimization, that final polishing step, significantly improves the overall motion quality. And crucially, it dramatically reduces the error in aligning the generated motion with the input pose constraints.
So it really helps nail those specific poses.
Definitely. And combining the pose adapter with this inference time optimization yielded the most coherent and accurately aligned dance sequences. It confirms they're both key for achieving precise, reliable editing.
Okay. They also briefly mentioned something about using shared datasets when training the motion tokenizer. What was the takeaway there?
Right. Their analysis indicated that training the motion tokenizer on a combined dataset mixing motion data from human ML3D, AST++, Gamin, and Fine Dance actually led to noticeable improvements in both how accurately it could reconstruct motion and the overall quality of the generated dances, especially for medium-sized codebooks.
So learning from more varied data helps.
It suggests that learning a shared vocabulary of basic motion building blocks across different data sets can be beneficial. It helps the model represent and generate a wider range of dance styles.
Interesting. But not too big a vocabulary.
Yeah. They did note that using an excessively large codebook could introduce redundancy and potentially have a negative impact. So again, a balance is needed.
And finally, they looked at the number of iterations for that confidence-guided sampling in the music adapter, the resampling step.
Yep. Their experiments showed a trade-off there. More sampling iterations generally improved quality and diversity.
But took longer.
Exactly. More compute time. They found that beyond around 18 iterations in their setup, the improvements started to level off while the runtime kept increasing.
So another sweet spot. Find the right number of refinement steps for good quality without waiting forever.
Precisely. Balancing output quality and generation efficiency.
Okay, so bringing this all together, it really sounds like DanceMosaic represents a significant leap forward in this whole field of automatic dance generation.
Absolutely. I mean, it marks a substantial advancement, not just for high-fidelity, efficient generation,
Right.
but maybe more importantly for adding those robust and versatile multimodal editing capabilities. That's been a major bottleneck in previous approaches.
Yeah, the ability to generate realistic, diverse dances that are synced with music and can be easily edited using text and pose constraints, that's a really powerful combination. The implications seem huge.
Indeed, it really unlocks a wealth of possibilities for creative industries, doesn't it?
Oh, totally.
Imagine the new tools this could give choreographers for just rapidly prototyping and refining ideas.
Yeah, or animators creating super nuanced character movements.
Right. And content creators in VRR building truly immersive, interactive experiences.
And just digging into the details of DanceMosaic's architecture, the training process, it gives us a really valuable insight into the challenges and, frankly, the ingenious solutions being developed in AI motion synthesis. It's not just about making a figure dance, is it? It's about modeling that complex interplay of movement, music, style, and human intention.
Precisely. And it really prompts you to think about the future potential. How might this kind of tech further revolutionize how humans interact with computers?
Right.
And maybe unlock entirely new forms of creative expression in movement-based arts. Perhaps you, the listener, might find it insightful to check out the visual demos linked in the research paper.
Yeah, seeing it in action is probably key.
Definitely. It gives you a much more tangible sense of what DanceMosaic can actually achieve. It certainly provides some compelling food for thought about the evolving relationship between AI and human creativity.